Our next presentation is from Francisco Penedo, and he's going to be talking about guiding motion planning with language.
Thank you. Hi, my name is Francisco Penedo, and I'm going to present this joint work with Christy Basile and Colin Belta, titled Language-Guided Sampling-Based Planning Using Temporal Relaxation. So as a motivation, consider dynamical systems, such as one of these new Amazon delivery drones, operating in an environment with some delivery areas, A, B, and C, and some obstacles that I'm painting in red, which has to satisfy the specification, make deliveries in A, B, and C in this order for some specified duration and within some required deadlines. So we'd like to design an algorithm that can solve this motion planning problem while facing these two challenges. First, we want to be able to generate a best effort plan when presented with an unfeasible schedule. And we also want to deal with systems in high dimensions, potentially allowing us to generate plans, for example, for multiple drones at the same time. So in this work, we'll use time window temporal logic, or TWTL, previously developed by Vasily and Aksaray, to formally define the specifications for our system. So TWTL formulas encode words with values in a finite alphabet, and have this syntax that I'm showing here, where the Boolean operators behave as usual, and we add three temporal operators, hold or service S for D, which is satisfied if the atomic proposition S is satisfied in D time units, phi1 within A to B, which is satisfied if the formula phi1 is satisfied in the time window A to B, and the concatenation operator, or phi1 then phi2, which is satisfied if phi1 is satisfied and immediately after phi2 is satisfied. So you can see the motivating example here with the translation to the TWTL syntax. Now, the two important features that we're interested in for TWTL is that first, the formulas have an associated deterministic finite state automaton, which we can compute, and it works similarly to the Booke automaton for linear temporal logic. Second, we can easily define a notion of relaxed satisfaction of a specification by allowing delays on the timeouts for the within operators, like I'm showing here for the example. So our problem formulation will look like this. We have a dynamical system in discrete time with an admissible control set, a TWTL specification, workspace with some obstacles, and the problem is to find an admissible control policy such that the closed loop system is collision-free and satisfies the specification. Now, if the specification is unfeasible, we want to satisfy the relaxed specification that has the least accumulated delay. An important assumption I'll make here regarding the types of specifications that we're allowing is that the structure of the formula should look similar to this example here, where we have several concatenated tasks, which themselves do not contain any concatenation operators. Now, there's a wealth of literature related to this problem and its variants, and you can see some samples here. I mainly want to point out that most of the works that allow best effort plans for unfeasible specifications in some way do so without considering explicit time constraints. I'd also like to point that some ideas that we'll use here, such as combining sampling-based methods with automata-based techniques, were also explored before. For example, this work by Wolf, or this one by Vasily. So our approach is a sampling-based algorithm based on RT star, in which we keep track of our progress towards satisfying the specification by attaching to each node in the RRT tree the state indefinite state automaton that corresponds to the path from the initial node. So you can see this idea here representing this figure, where I'm considering this simplified specification with this associated FSA, and the nodes on the RRT tree are represented in different layers that corresponds to the attached state in the FSA. Now note that if we want to add a new sample to this tree, we need to pick both a layer here and a point in the workspace. So from the point of view of automata-based techniques, you can also view this process as incrementally building the product automaton between this FSA and the transition system given by the RRT tree. Now, for the optimality part of the RRT star algorithm, we use as our cost function the accumulated delay, which you can see computed here for the example. Now, this ensures that we either end up with a satisfying path with 0 delay, or we obtain a minimally delayed path. Next, we propose the language-guided biasing scheme divided in 2 parts, which you can view as exploration and exploitation phases. First, we try to quickly find a satisfying path disregarding any deadlines by biasing our sampling towards a final state of the FSA. Once we obtain this candidate path, we can compute which segment of the path has the worst delay and improve it by adding more samples to the layers in which it is contained. So you can see here, for example, for this candidate path in black, the worst segment is the one from A to B. So we added more samples to this to the layers in which it is contained, eventually finding a improved path with less accumulated delay. So let me show you some performance results for simulations. First, for the running example that I've been working with, which is a 2D workspace and a fully actuated point. It took about 61 seconds to find a satisfying path, where for comparison, when we disable our biasing scheme, it took about 4 times as much. We also applied a partition-based approach previously developed by Vasily and Aksaray, which only took about 1 second to complete. Now, this is not very surprising since the system abstraction that it needs to compute is very easy in this example here. However, for the 10D workspace, we considered a more complicated specification where the system can service either B or C after servicing A. And our algorithm took about 1 hour to complete, while the partition-based approach wouldn't even fit in memory. Now, this high-dimensional example highlighted some limitations and challenges that I'm going to show here. So first, there's a key improvement, a key performance improvement for RT algorithms where the search radius for neighbors is reduced as more nodes are added to the tree. However, we cannot actually apply this optimization to our algorithm due to the discrete time nature of our specifications. Second limitation is that our biasing scheme can be counterproductive if the areas of interest have large volume. So as an example for this problem here, where we have a first task with a long deadline, but which can be serviced in many different places, if we complete this task far away from the second one, the next deadline becomes unfeasible. However, our biasing scheme will still try to improve this path because it has this segment because it has the worst delay, instead of trying to find a better first segment like this one here, for example. So to conclude, we proposed a sampling-based algorithm for motion planning with TWTL constraints and a biasing scheme that is guided by the specification. It generates RT star completeness and optimality for regarding the accumulated delay, and it can handle high-dimensional configuration spaces. As future work, we would like to consider a larger fragment of TWTL in which the specifications are allowed to have subtasks or recursively have concatenation operators. So that's all from me. Thank you for your attention, and I'll now ask any questions.
Hello. This was a great piece of work. One of the first questions I had, you glossed over this very quickly. When you say you have a biasing scheme where you create initial paths with no time constraints and then use them to create further plans with time constraints going forward. How much does it help, especially in cases where optimal solutions may not be, like the solutions with time constraints will be drastically different compared to the solutions that would exist in like your biases, initial biases?
It's sort of related to this second limitation that I'm showing here. Your question, we actually encountered it when, in this case, if our candidate path would be this first red one, the second path is sort of fundamentally different in that we cannot actually improve the worst segment of the path and then reattach to the rest of it. We actually need to find better paths before or even after to actually complete it. We couldn't really find a good way to overcome this limitation, and in those cases, yes, actually biasing could be counterproductive to finding the optimal solution.
Other questions?
If there are no other questions, I do want to ask, you also mentioned that during the RT sampling in
Yes.
the tree, there is, yes, you have to sample both in space and between the finite state automata. Could
Yes.
you comment on that? It is slightly unclear.
So once we, so let me show you as an example here. In this layer of the path, in this layer of the tree, we're actually computing, let's say, a path between this A region to the B region, which corresponds to being in this state of the FSA. So basically in the specification, we've already completed A, or serviced A, and now we're moving on to complete B. So in order to add nodes to this whole tree, we need to tell the algorithm this point, where do you want to be able to connect it from? So do you want it to be a node in the path between A to B, or do you want it to be from B to C? So we need to both sample this. We need to pick both a layer, or equivalently, we need to pick which state will be attaching to the node, and then picking a point in the workspace. And then we now know which other nodes we can connect to. So here, if we sample a point here, we'll only look at neighbors in this layer instead of the other one.
Any other questions? If not, let's thank our speaker one more time.